So let's move on with our second panel of the day, navigating the energy transition, innovation and challenge in distribution system. So it's now my pleasure to welcome Julia McNally to the stage and our panelists. Julia is the Director of Climate Action at Toronto Hydro, where she leads a dedicated team helping customers achieve their decarbonization goals. She's also a valued member of our Knowledge Mobilization and Policy Impact Technical Advisory Committee. Julia will be moderating this session, and this session is sponsored by Toronto Hydro, and I want to thank them for their support for this year once again. So Julia, this floor is yours.
All right, amazing. Thank you, Edward, for this opportunity. And I want to thank Edward particularly because for the last year and a half since I've joined Toronto Hydro, I have been on his case saying we have to focus on the distribution system. So I think to get me off of his case, he agreed to create a panel focused on the distribution system. The reason I wanted to do this is because in my experience, we focus a lot on the bulk system. We talk about transmission, but we are not going to be successful in the energy transition if we don't also address the distribution system and really understand the opportunities, the challenges, and the dynamics. So we have a fantastic panel here today. As you will learn over the course of this hour and a half, they are very expert and they are also outdoorsy athletes. Just stay tuned. And they're going to touch on topics like how do we meet peak when all buildings are electrified? And how do we integrate solar effectively? And how do we account for the physical and financial limits and opportunity of solar and batteries? So just to give you a sneak peek, the panel is going to dig into some of these issues. As with the previous session, we've got 5 speakers. You can see, you can count. They will each present for about 8 minutes, and then we'll have an opportunity for questions. So we are going to start with Brian McMillan, who currently works with CanMet. Brian brings over 45 years in the electricity sector, including time at Ontario Hydro. And for those of you who are not in Ontario, Ontario Hydro continues to be the most popular energy organization in Ontario, even though it hasn't existed for 24 years. So fun fact about Brian. Brian is an avid snowmobiler. He bought a snowmobile last year. Less fun fact for Brian is that although he lives in Sudbury, Ontario, deep in the snowbelt, he wasn't able to use the snowmobile trails last year because there wasn't enough snow. So sorry, fun fact with a less fun fact. Brian, over to you.
Good. Thank you. I'm going to speak on my experiences with the practical applications of models. So we're going to go right down to all the stuff that you're doing now, 15 years from now will be in my lab or my successors' labs. And that's what we're going to talk about a little bit. We're going to talk about how distribution systems are designed and some of the limitations and some of the challenges that they're going to face in the world where, as David Rosenthal said, that we want to electrify everything. That scares the heck out of a distribution engineer right now, I'll tell you. So we're going to talk a little bit about that, and I'm going to tie in. All right, there we go. I'm going to talk about this subdivision, as we get along. But I'm going to tie in some of what the opening speaker said. I'm not going to go that far ahead. We're going to stick there for a minute. Andre Bernier talked about evidence-based models. So we're going to present to you the practical application of an evidence-based model. He talked about the change to net zero requires a much faster pace. I'm going to speak on that, and I'm going to speak on the financial implications of that from operating a distribution utility in the province of Ontario, what that means. Drew talked about performance characteristics that are not based in historic evidence. We're going to need some of those. We have to project into the future. What do the future loads look like? How are they going to impact the assets in the distribution system? And David Lazelle talked about past transformational changes and how we may be able to learn from those. And I think there's some important lessons there. And I know you had a few examples up there, David. A couple that weren't up there, but I think are relevant to what we're talking about. the municipal electrification effort in the early 1900s, and the rural electrification effort in the post-World War II period, both of which required, I think, government intervention to be able to move forward. We're going to talk a little bit about that. David brought up a question about guardrails around electrification. I'm going to talk about handcuffs. Cost, equipment, labor, and designing. We lack in all those things going forward to build the distribution system as it will be needed. So let's talk a little bit about standards, a little bit about how distribution systems are designed. In Ontario, there are about, and I'm going to speak about the Ontario model because it's the one I'm most familiar with. In Ontario, there are 50 plus local distribution companies. All of them except the smallest three use something called USF, Utility Standards Form Distribution Standards. That's how we design distribution systems. We don't do it similar to bulk system. Bulk systems are engineered in one-ofs. Distribution systems are built from models, basically. They provide the distribution standards used to design all the underground and overhead lines in the province of Ontario. There's some significant advantages to that. You can think back, for those of you that are old enough, to the late 1990s when we had an ice storm and in Ottawa, and all the utilities had to converge here to rebuild the system. The fact that it was all built on standards meant that you could take linemen from southwestern Ontario and put them in here, and they could rebuild the system without a problem. Mute your phones. So that's how we build systems. It's significantly different than transmission systems, as I said. And I had the privilege of being on the team that helped develop the USF standards. So I have some significant knowledge in how they were put together. So let's talk a little bit about distribution transformer loading and the methodology based, which put together evidence-based models. So here's a typical subdivision in province of Ontario. And we're going to talk about this subdivision. It was built back in the 1970s. We're going to assume it was 1975. I have the schematics for it. There's 62 single-family dwellings in it. Probably based on the transformer sizes that I see, there was electric baseboard heating or a central electric heat in these homes. In some of them, they're about 1,500 square feet each. And if you look at the little chart that's there, you're going to see that there are 6 transformers feeding it, 100 kVA down to 50 kVA. The number of customers on each varies between 14 and 6, and that's a pretty typical design for an existing subdivision or in the province of Ontario or anywhere. I think, Hydro-Quebec, Nova Scotia Hydro, they would all agree with that. You'll see the little drawing there. We're going to talk about what's going to be needed when we electrify that subdivision. So it's built 1970s. People live there. They're going to live there for years. The 3-phase overhead line probably we won't touch. We're going to have to rebuild that single-phase underground primary. It was put in the 1970s. It's direct buried. What does that mean? It has no duct. If you want to replace the cable, you dig it up. That's what you do. Pad mount transformers, there's 6 of them. We're going to increase that to about 10 based on having electric vehicles and electrification of the homes and getting rid of the gas heat. And those transformers feed, I think it's 3 or 4 handholds. So there's a main secondary bus which goes to a handhole and then services to each house. The number of handholds will change. The number of handholds will increase. They'll be moved. All of that means that the lovely subdivision that these people live in is going to get dug up and rebuilt. So let's take a look at how that might happen. Let's look at it after electrification. So one of the things I didn't tell you was the standards. So what happens in the standards? In the standards, if I'm handed basically a drawing of a subdivision, it's a road with a bunch of lots. I'll ask some questions. I'll ask, what kind of homes are going to be built there? What's the heating source? And what's the square footage? And those things are all factors that are used to work from the standards to come up with a point system. The point system is added up, and the number of points defines the transformer size. And it's all based on the load profiles that you modeled or somebody like you modeled somewhere in the past and put down and created this system to make it easy to design a subdivision. But that, of course, is based on this subdivision now. If I look at it, it would be based on gas heat, 1,500 square feet, single-family dwelling, and probably 50% of the homes in Sudbury would have central air, maybe, give or take. What happens when we add electric vehicles? What happens when we electrify that and put a second-generation heat pump in it? What does it look like? Well, what happens is the points go through the roof. And it's all based on the models that we currently have. The USF standards were revised in 2021. And the model that they had then basically produces a very undiversified load when you add electric vehicles. Most of the load occurs around 7 p.m., looks like to me. And what that means is that you have a very large peak on that transformer the more electric vehicles you add on it. So if you look at these homes, 62 of them, you change it to 100% with second generation heat pumps. You add one EV with a 12.6 kV level 2 charger with load control, and you have 50% of the homes have a second one, which isn't unrealistic. If you take a drive in your neighborhood, how many driveways have 2 cars in them? A number of them. So you look at that, you add up the points, you get to the right side there, the transformer design loading with the new point system would be quite high. What are we going to do? What do we have to do? We're going to have to rebuild this system, basically. What does that look like? The peak load on this 62 homes looks like it increases from about 150 kVA to around 1,500 kVA. To accommodate that, we're going to add 4 transformers. We're going to increase the size of the transformers. We're going to convert the direct buried single-phase primary to a 3-phase induct, and we're going to increase the primary wire size. The cost to do that would be about $9,000 a lot. We talked about speed. We talked about cost. We talked about the transformational efforts of the past. This is going to need a transitional effort. The distribution system as it's funded today typically is rebuilt on a 25 to 40-year cycle. If you want to rebuild it faster than that, you have to get money from somewhere. It's either going to have to come from government or rates. This tells us it's going to be significantly expensive, and we're going to have to look for sources for that money. I'm just about out of time, so I think I'll wrap up. The second thing I wanted to point out was equipment, materials, and designers. The current lead time for a power transformer, which would be 10 MVA or greater, is 36 months. The current lead time for a distribution transformer is somewhere between 40 and 58 weeks. The current lead time for underground 25 kV switchgear is 68 weeks. This is not a good scenario when you think about trying to rebuild the system in a short period of time. We're going to need to take some action. Thank you.
All right. Thank you, Brian, for setting the stage in a really practical way. So following up on that, we have Michael Swift, who is also from the distribution, from a distribution utility. Michael's a distribution engineer at Hydro Ottawa, focusing on the energy transition and focusing on some of the challenges and opportunities of it. In Michael's spare time, he is swift, riding his bicycle up and down mountainsides in BC, over things called enduro trails in Quebec, and over freshly fallen snow. Hope you can find that this year, Michael. And so let me pass it to Michael, who is going to talk about some of the work he's doing at Hydro Ottawa.
Thank you, Julia. So I'll start by saying that Brian did a fantastic job of explaining what it looks like on the ground level. I'm going to take a bit of a higher view and show how local LDCs, local distribution companies in Ontario are now navigating that energy transition, specifically for us at Hydro Ottawa. I'll start with a very brief overview of what we look like in terms of our service area. We cover all of Ottawa as well as Castleman. We have over 350,000 customers, 91 transformer stations, and to Brian's point, that's going to be increasing. Over 2,700 kilometers of overhead lines, over 3,200 kilometers of underground assets. It kind of paints a picture. We have a very good, solid asset base. We have a good number of customers. And historically, we've been a summer peaking utility. Other than the dip that you see there due to COVID, we've usually sat around 1,450 megawatts of air conditioner summer peak load. And with the transition and decarbonization, we are now going to be moving into a winter peaking utility. Thank you. So that is mainly driven by these factors here: residential and commercial energy use, primarily space heating, and today done with natural gas. As we move to electrification through decarbonization, that shift is going to push us towards a winter peak, and a significant one at that. And with that come a few challenges. From a modeling perspective and forecasting, one of the biggest challenges that we have, especially in the Ottawa area, is uncertainty around the performance of heat pumps in extremely cold temperatures, which we consider at minus 10 degrees or below, and that's where we see efficiencies drop off significantly. For us to actually forecast out from that, we had to create some scenarios for the decarbonization policy adoption, and my next slide will speak to that. I do want to point out that we also took into consideration meeting the Government of Canada's electric availability standards, with 60% of all new vehicle sales for light-duty vehicles by 2030 being EV and 100% by 2035. Our forecasts and models also assumed electrified medium and heavy-duty vehicles, as well as the electrification of the Ottawa public transit system. The reason I point that out before we jump into the scenarios is that there's also uncertainty around the EV charging, specifically with the shift to a winter peak. So with the winter peak, we're now going to have the air source heat pumps and electrified heating, and we have limited range with the electric vehicles. How does that look like from a charging profile perspective, and how does that play into a forecast? So these are the scenarios. Before I jump into them, I do want to point out that each of these scenarios achieves Canada's goal of net zero by 2050. What differs between them is at what pace that's met. And so to the far right is the base case extreme case, which is where we really hit all of the policy-driven targets. They're quite aggressive. They're very enthusiastic. And by that, that means that it would be the largest amount of system investment at the shortest time period. We also explored a moderate scenario where we took that policy-driven scenario and we grounded it in what we call kind of our reality. What information do we have from our customers today? What do we see from now 3-5 years out in terms of EV adoption, installation of chargers, air source heat pumps, and retrofits in homes, and kind of taking that policy-driven and adjusting it accordingly so that we see where we are today and move forward. Again, I want to stress we do hit the target by 2050. It's just an adjustment there. And within that moderate scenario, we have a moderate A and a moderate B. Moderate A assumes 50% of the space heating, which again is the primary energy use, is electric air source heat pumps, with 25% being electric resistive heating and the remaining 25% being low carbon gas. So that kind of captures a transition where customers are moving over to electric, but we don't have the technology there just yet to meet the air source heat pumps at 100% below minus 10. Moderate B assumes 100% of the space heating being done by electric space heating through air source heat pumps. There was also a sensitivity analysis included for the scenarios, high and low. High being, again, the policy-driven decarbonization, but very enthusiastic adoption, and all the timelines moved forward, and low being a delayed adoption of the policy. Unfortunately, I'm unable to share with you today the actual forecast, as we are going into a rate application with the Ontario Energy Board. So I can speak to the scenario formation, but I can't share the forecast at this point in time. Once we go through our rate app, we'll be able to share the forecasts. I do also want to touch on distributed energy resources at Hydro Ottawa as a touch point in that energy transition in the field. We have 140 megawatts of renewable energy in our system today, over 1,400 sites of PV solar totaling 50 megawatts, 21 hydraulic sites totaling 88 megawatts, 3 biogas sites totaling 1 meg. We have also 2 megawatts of energy storage spread across 5 sites in our area, and then rounded out by 25 megawatts of non-renewable, mainly natural gas, followed by diesel and petroleum. And I included a map here showing where we have clusters of our projects. Blue is renewable, orange is non-renewable, and green is energy storage. The reason I wanted to highlight that was to show that there's areas where there's quite a dense collection of DERs. And That's important from a utility perspective because we start to potentially see constraints in our system, and I kind of want to touch on those right now. So there's a few integration challenges that we face as a utility, and as a distribution engineer, we have to consider all of these when we want to connect new distributed energy resources. A large one is the short circuit capacity on our system. As we connect more DERs to the system, they cause more current to flow through, and if there's a fault condition, those currents from the DER can now feed into the fault, which can exceed equipment ratings and cause failures. We have thermal capacity constraints as we add more DERs on the system, and now there's more ampacity flowing through the existing infrastructure. We can start to overheat the conductors, we can start to overheat equipment, and you can reduce the effective life, but you can also cause premature or immediate failure of equipment. There's reverse power flow considerations. As we connect DERs, traditionally, we have from the utility side going to the customer for energy flow. Now we're going from the customer with a generator flowing back onto the grid. Not all of our equipment is designed and able to accommodate the reverse flow. It can cause circulating currents that then reduce the life of the transformer or again, cause failure of that equipment. There are many power quality considerations as an engineer that we have to consider from anything harmonics, phase imbalance, voltage instability, and flicker. And again, as we have more DRs connect, especially in clusters, that's compounded. And then lastly, we have anti-islanding consideration, which does have power quality issues, but even more so safety. We want to ensure that when a DR is connected, especially in higher concentration, that they are not operating unsanctioned if there's a loss of the utility supply for safety reasons. Each of these, there are ways to address them. From the short circuit capacity perspective, we have everything from opening our tie breakers at our stations to installing bus tie reactors. There's fast switching schemes with new technology that we can apply. For thermal limits, we can do load transfers and upgrade the conductor equipment. To Brian's point, all of this costs dollars. All of this requires coordination, and especially with a higher penetration and the transition to more DRs on the system, we need to have that visibility into where to make those investments. With respect to reverse power flow, we can upgrade that equipment, or we can start to adjust loading on those feeders. Power quality considerations, we highly stress meeting the CSA and IEEE standards in order for that equipment to have the minimal impact on our systems. And for anti-islanding, we currently at Hydro Ottawa require the installation of transfer trip for DERs so that they can go offline if there's a loss of the utility. We're also exploring using reverse power flow protection to protect our system as well as the customer's generating site. So I hope that gave you a good overview from the utility side. We got a detailed ground view with Brian. This gives you an overview from the utility perspective, and I'm excited to discuss more in the forum. Thank you.
All right, thank you, Michael. So now we're going to shift over from the on-the-ground utility perspective to hear from our modelers. So first up is the modeler, Jeremy Keene, who comes to us from Denver. Thank you, Jeremy. Jeremy is a senior research engineer at the National Renewable Energy Lab, NREL, and he works on the Distribution Edge Group. Jeremy has a PhD in engineering and public policy from Carnegie Mellon. Jeremy's fun fact is that after university, he volunteered in Lesotho, where, following our theme, he participated in a half marathon in Cape Town and then skied in the Maluti Mountains. Where, you ask, are the Maluti Mountains? Well, they're just north of Lesotho in South Africa. So, Jeremy, welcome.
Great, thanks. So I'm going to talk about some considerations for improving distribution capacity planning studies, and to kind of differentiate what I'm talking about with what the previous speakers have talked about here. The focus of this talk is really on large system studies, trying to look further into the future, 5, 10, 30 years into the future, and trying to understand, what kind of investments we need to make in our large investments, our substations, our feeders, transformer replacements, and the like. So first off, what are some options for scaring policymakers when we do these kinds of studies? So I've shown here on the left a news article about a report that was done by Kivala in California, estimating $50 billion in costs due to electrification. And the way they went about this, I think, was a practical approach and really kind of similar to the dialogue we're having now and how we want to go about electrification studies. They were able to build topological models for the entire state of California, no small task, right? Where they then aggregated different load profiles up at sort of different kind of fundamental levels in the distribution network, the secondary networks, the feeders, and the substations. And they used those changes in load profiles to understand kind of what kind of investments would be needed for the system. So it was a good study and opened up a kind of a lot of room for kind of honest dialogue about how we could do this better. And that's what this slide is about. So for example, some omissions that can lead to exaggerated costs, which I think this cost is a little bit exaggerated, are emissions that could lead to that are things like not including low cost options for managing load, right? Like demand side resources. Not giving the rates associated with these kind of investments. Right? Electrification is expensive, but there's also going to be a lot of kilowatt hours that are sold associated with electrification. So the end cost to the customer may not be as drastic as we think. And then finally, kind of the hardest one to talk about, and I'm going to spend more slides on this, is trying to include the fact that utilities are going through a kind of a very strategic decision-making process, not just for electrification and loads, but other things like replacing aging assets and damaged assets and reliability and so forth. And so to go talk about that, I'd like to just give like a very simple description of a sort of typical distribution capacity planning process. This is cartoon. If you'd like to kind of learn more about this, there's links to some NARUC work on this, and as well as a white paper that I did at NREL on the distribution capacity planning process. But the sort of key steps here are, kind of and we actually saw Michael's work going through some of these steps too, but sort of formulating what your objectives are, like, decarbonization, reliability, safety, and so forth. Defining your scenarios, like we saw in the last presentation, going through a load forecasting process and needs assessment and sort of a solutions identification. And typically, these are repeated on sort of like a 5-year planning cycle. It varies with utilities. But here's the thing I want to point out. If your scenarios only look at electrification, and if they only look at overloading, they miss high solar adoption and increasing major event days from sort of natural hazards. They don't look at end-of-life replacement cycles and so forth. Then ultimately you're going to come to a conclusion that says electrification leads to a lot of cost, because you're essentially attributing all future costs just to electrification and not other things that are happening. The other thing that I kind of want to point out is, we're talking about sort of long-term strategy here. And this sort of 5-year planning cycle that many utilities are using may not be adequate for truly strategizing about our sort of investments into the future. So let me give a couple more examples of why we need to think a little bit more strategically and long-term in our distribution capacity planning process. So voltage class upgrades, transitioning away from natural gas, deciding if you want a DERM system, which then enables a lot of other technologies for managing solar. Trying to deal with really constrictive budget constraints in the distribution capacity planning process, and trying to look at the co-benefits of resilience investments. All of these things are really messy problems that require kind of a lot of strategizing about the best path forward for making capacity planning investments. Then there's non-wire alternatives, which have been really unsuccessful in the I'd say the past decade. So here's a news article from California showing that they haven't been able to deploy a lot of non-wire alternatives to defer capacity with distributed energy resources like batteries. And I would argue that this is also kind of a symptom of the fact that we don't have a very strategic process of going about our long-term capacity planning process. So like the typical non-wire alternative process, for example, it doesn't include some typical utility planning processes, like evaluating least cost options such as switching to manage load and transfer load between different feeders. It doesn't include the value of resilience that distributed energy resources can create. And it doesn't really include the value of what I call like the optionality value of distributed energy resources. If you're trying to think about how you might right-size investments looking into the future, distributed energy resources can help sort of with that right-sizing process, and so there's an uncertainty associated with load into the future, and distributed energy resources can help manage that uncertainty when we're trying to make these large decisions. Okay, so how do we get there? How do we get to a place where we can make longer-term strategic distribution capacity planning decisions? Well, Can we just reach into our tool bag at NREL and dust off some tools and apply them to this process? Let's take a look. Okay, so we have a lot of load modeling tools at NREL. We have load modeling tools for electric vehicles. Those are Tempo and EVIX. We have distributed generation propensity adoption tools like DGen. This looks at solar and solar plus battery adoption. We have other building modeling tools like Ochre and Comstock and RevStock, and various ways to sort of aggregate all of these load profiles. But these just tell us what the impact is on our load profiles. They don't tell us kind of what our strategy should be moving forward over a long period of time and what the best kind of investments are to make. I come from the Distribution Edge group, and we have a whole host of tools. We have hosting capacity tools like Disco, which can run hosting capacity across service territories and even make some suggestions for investments in sort of the interconnection of distributed energy resources. We have interconnection tools like Precise, and we have resilience tools like ERAD that can run threat simulations to see how the distribution network is affected and how customer outages occurred. We have no way of sort of taking all of these different tools together and doing a needs assessment to see, again, what are the co-benefits of investing in distributed energy resources versus just investing in distribution automation or just investing in larger substations and trying to develop a long-term strategy that sort of meets all of our objectives. Okay, so how are we going to then address that problem? The tool that we've been developing over the past year and further developing this year is called Cadet. It's a distribution capacity expansion planning tool. For those of you familiar with capacity expansion planning at the bulk grid, this is in many ways analogous to that tool, those kind of tools. So this is an optimization tool. In fact, it's a hybrid, heuristic, and mathematical optimization tool. And in many ways, it simulates the distribution capacity planning process. It allows you to have decision variables like the size of a transformer, the placement of distributed energy resources, and then sort of looks forward under some arbitrary planning horizon and helps with the planning decisions that could be made over that planning horizon. One of the important design decisions that we made in the development of Cadet is that there are so many distribution capacity planning use cases that can be sort of devised in this sort of world, right? We can look at hosting capacity. We can look at non-wire alternatives. All of these require different modeling fidelities for the capacity planning problem that we're doing. And so we've sort of devised a sort of a building block architecture, very low level process for formulating these problems and applying them to different use cases. The only problem with that is now we've made a complicated problem, and we've taken a complicated problem, we've made it even more complicated. So the diagram that I'm showing on the right here shows the sort of typical workflow for the studies that NREL does for various clients. This one in particular was for the city of Los Angeles for the LA 100 study. And you can see that there's a large number of interdependencies between the different analysis tools that we have. And so we've developed a lot of tools to help manage that complexity. Helix is a co-simulation tool. MDO for Grid is co-optimization, and DS Grid and Pipes. Pipes in particular helps manage the handoffs between different analytical processes that we have in an overall workflow. So with 8 seconds to go, conclusion, distribution capacity planning studies can be misinterpreted, and the US national labs are developing a lot of tools to sort of help with that and manage the complexity that we have. Right. 1 second to go. Yeah.
Thank you, Jeremy, for landing that. I would point out that there's a shaming timing tool here. It doesn't just stop at 0, it starts to count how long you've gone over. So that's cool. Thanks, Edward. So next up is Jotham. Peter's also a modeler. So Jotham is managing partner at Navius Research. And he specializes in energy economy models and the analysis of energy and climate policies. Fun fact about Jotham, he is an avid runner, I might say an extreme runner. He's not content with just running around the block. He likes destination runs. And when I think destination run, I think Caribbean, but not so much with Jotham. He thinks hypothermic run, half marathon in Winnipeg in the middle of winter. Anybody who wants to join Jotham on the run, please speak with him after the session. So over to Jotham to talk about how they're using their modeling on the distribution level.
Thank you so much. Thanks for inviting me to speak here today. The main objective that I have for today's talk is to summarize some of the research that we've done to explore the implications of achieving deep reductions in greenhouse gas emissions and how these might affect Canada's electricity system. I have a couple of different objectives for today's talk. The first is to convince you, if you're not already convinced, that achieving deep reductions in emissions will likely require a significant electrification of the economy. The second objective is to acknowledge the fact that this electrification is likely to increase peak load. However, when we're looking at the peak load impacts of electrification, it's very important for us to put these impacts into context. So for example, if we see an increase in peak load that's accompanied with an increase in electricity sales, that increase in peak doesn't necessarily need to be quite as scary. And finally, there are technological options which are either currently available or that are emerging, which can help utilities manage this increase in peak. In terms of what I'll do today, I'm going to very briefly summarize the challenge of electrification and why we should be scared about peak load. I'll offer some key insights and then some conclusions. Just a little bit of background on Navius. We specialize in modeling the impact of climate and energy policy. The modeling system that we use is an integrated model where we provide an internally consistent framework with which we can look at both the economy as well as the different types of technologies available for households and firms to reduce their greenhouse gas emissions. And finally, we've connected this model with a detailed representation of the electricity sector as well. And the results that I'll be presenting here today are based on some research which we'll be releasing fairly soon in our Canada's Energy Dashboard, in which we explore 216 different scenarios in which Canada achieves net zero by 2050. So why is electrification, or why does electrification potentially impose a challenge for the electricity system? This figure here on the right shows the load duration curve for Ontario in 2015. And it shows that the consumption of electricity was quite variable over the course of the year. At its peak, it was in the range of around 23,000 megawatts, whereas at its lowest point, it was just a little bit above 10,000 megawatts. But one of the challenges associated with this from the perspective of the electricity system is that in order to make sure that you're meeting your electricity consumption on peak, traditionally utilities needed to have enough capacity to generate electricity as well as to distribute that electricity on that peak, in spite of the fact that a lot of that capacity may sit idle over the course of the year. However, the system's ability to recover these costs are more directly associated with electricity sales. And so therefore, if everything else being equal, we were to see an increase in peak load electricity consumption, we'd also expect to see a corresponding increase in electricity prices. And so what is the role for, or what is the implication of achieving net zero on electrification? And I think that the role that electrification will play in achieving net zero is really best exemplified in two end uses, residential and commercial space heating, as well as the demand for light-duty vehicles. Just to put these two sectors and end uses into perspective, in 2015, buildings accounted for about 71 million tons of carbon dioxide. That's about 10% of Canada's total, of which the vast majority of this comes from space heating. Whereas the demand for light-duty vehicles accounted for about 84 million tons of carbon dioxide, or equivalent, about 11% of Canada's total emissions in 2015. And when we look at a scenario in which Canada achieves net zero greenhouse gas emissions, we see that these two end uses largely electrify in response to that policy. Electrified space heating in the residential sector grows from about 35% up to over 90% by 2050. Commercial commercial space heating grows from about 10% electrified in 2015 to just a little bit under 80% in 2050. And then finally, the share of light-duty vehicles on the road which are electrified grows from negligible amounts in 2015 to almost about 80% or to over 80%. I think it's important for us to highlight there's some uncertainty here. We've looked at net zero under 215 different scenarios. And so the bars here show the range of results that we've seen in our analysis. And it indicates that, we still see a decent amount of electrification, but there's uncertainty in that. So the range of impacts that we see for residential space heating range from about 60% to about 90%. On the other side, for the light-duty vehicles, we see between about 30% and about 90%. And I can speak to the range if you guys like to in the questions. So what does this mean for peak load? This figure here on the right shows the peak load, or shows the 50 hours over the course of the year with the highest load in Ontario. It shows it in 2015 in a current policy scenario, and then in a net zero scenario in 2050. And we further disaggregate that load by end use. So the orange bars represent space heating as well as space cooling. Ontario currently has a space cooling load, or a space cooling peak. The solid green bars, or the dark green bars in the middle, represent electricity consumption coming from transportation. And then the blue bar at the bottom represents everything from refrigerators to industrial load. And it shows that achieving net zero leads to a significant increase in peak. In Ontario in 2015, peak load was in the range of around 23,000 megawatts. This grows to about 55,000 megawatts by the year 2050 under a net zero constraint, of which almost half of that is coming from space heating. About 25,000 megawatts is coming from space heating alone. Transportation grows from effectively negligible levels in 2015 to account for over 15,000 megawatts of peak load in Ontario. And finally, we're also seeing increases in load from other sectors as well. We're seeing increases in load from electrifying water heating, as well as some increase in industrial load growth. The final thing that I think is important for us to acknowledge, that it's not just net zero that will lead to this increase in peak electricity consumption. We also see this happening even in the absence of achieving net zero. The bars in the middle represent what we expect to happen under a current policy case or a legislative policy case. And even in the absence of achieving net zero, we're seeing that peak load is growing to almost 40,000 megawatts. And this is primarily driven by transportation. But there's options available to mitigate this impact on peak load. The first, and perhaps the one that I'm not sure if it gets discussed enough, is building energy efficiency. So I just want to quickly compare what we saw in Ontario from the last slide. Just keep your eyes on the level of space heating and what's happening in British Columbia in this slide. And one thing you'll see is that the low growth associated with space heating isn't nearly as significant in British Columbia as it is in Ontario, in spite of the fact that we see a similar level of electrification of space heating. Now, there's a number of different reasons for this. Heat pumps work more efficiently in BC than they do in Ontario on peak, but also shows the importance of building energy efficiency. The building codes in BC, as we've represented in the model, lead to a significant reduction in heat load per meter squared of floor space. And as a result of that, as this heat load is subsequently electrified, it doesn't have as much of an impact on peak load. It's also important to highlight that some of these sources of load are more evenly distributed over the course of the year. So transportation isn't as acute on peak load as space heating might be. And likewise, a lot of the industrial load growth that we're seeing also is more evenly distributed over the course of the year. And the final thing that I'll highlight is that there are new technologies that are emerging which can help manage peak load. And of these, I'm only going to look at one example here in this project, which is the role for utility-controlled charging of electric vehicles. Utility-controlled charging provides an opportunity to move electricity consumption off of peak hours and onto non-peak hours. And this leads to a significant reduction in peak load. So the solid green bars on the far right-hand side represent the total amount of electricity consumption coming from transportation with utility-controlled charging. And you'll see that it's a lot smaller. It doesn't mean that electricity consumption from transportation is lower. It's just being shifted off of those peak hours and onto non-peak hours. So the main things I'm hoping you guys will take away from this talk today is that we think that achieving net zero is likely to lead to a very significant electrification of the economy. And we do expect that this will raise peak load in Canada and within every single province. However, there are ways available to mitigate this increase in peak. The first is that more stringent building standards can significantly reduce impacts on peak load. And second, a number of new technologies are likely to emerge
which can help manage peak load. We've looked at utility-controlled charging here, but there are other opportunities for utility-controlled charging of different technologies, smart thermostats, thermal storage in buildings, et cetera. Thank you.
Right, excellent. Thank you, Jotham. And last but not least, Amara Slaymaker. Amara is a consultant at Dunsky Energy and Climate Advisors, and she leverages expertise in the energy sector, particularly focused on renewable energy policy, data analytics, supporting utilities, governments, and others. Fun fact about Amara. It won't surprise you, given the theme of this group, is she is an avid outdoors person and hiker, and she has just returned home from 3 weeks hiking in Patagonia. So Amara, hope you're not feeling too much withdrawal, and thank you for your. Thank you.
All right, thanks. Hi, everyone. My name is Amara, and I work for Dunsky Energy and Climate Advisors. As mentioned, we're a consulting company with the mission of accelerating the energy transition. And today I'm going to be talking to you about some insights that we've gained from supporting our clients and helping to better understand and plan for distributed energy resources, or DERs, particularly through potential assessment, as well as benefit cost analysis. So as has been touched on by some of the other panelists, why are we talking about DERs? They can offer an interesting solution to some of the emerging challenges that we're seeing on the grid. For example, supporting with mitigating peak impacts and providing resource adequacy needs. They can act as non-wire alternatives to help avoid or defer infrastructure investments, and they can even support with the integration of renewables. Similarly, they also offer an interesting value proposition. They can be cost-effective in many cases. They are quick to deploy relative to some traditional wires and poles options, and they can be right-sized to avoid the risk of overbuild while still remaining scalable. So, they are a potential solution and have an interesting value proposition, but that's not to say that there are not still barriers out there to really unlocking and tapping into this potential. So DERs are not always properly considered in planning processes, may not be valued or eligible to participate for all of the benefits they can offer, or are simply not coordinated across the different levels of the system. And we're going to need solutions across all three of these pillars, so planning, enabling, and integrating, to really tap into this potential. But today I'm just going to be focusing mostly on the planning side. And specifically within this, looking at potential assessments. So how can we kind of understand when, where, and how many DERs could be showing up on the system? Looking at evaluation frameworks. So how can we actually understand the different costs and benefits that DERs can provide and evaluate them compared to other resource options or infrastructure? And then finally, kind of underscoring all of this is coordinated planning, which can help us to have a more holistic perspective on the broader system needs and then really capture this full value stack from DER deployments. So first, regarding potential assessments, our work has really highlighted that there are several critical nuances that need to be captured in order to have a full understanding of what the impact could be to the system. The first is that potential is both location and time sensitive, so it depends heavily on the load curve shape and peak periods, which might not be the same from year to year as your load is changing and more technologies are coming onto the system. And it might not also be the same from feeder to feeder, for example. So this is one important factor. The second is that impacts to load shape are diverse. So DERs are not all one thing, and they don't all have the same impact to our load curves. Some may offer a simple peak reduction, whereas others may be more of a peak shifting mechanism where we have to take into account potential recharging and rebound effects. And due to this, DER potential is not necessarily additive. So there are these rebound effects to take into account, as well as interaction between all of the different types of DERs and other technologies, which all have their own impacts to the system curve and must be considered in order to avoid potentially creating unwanted effects such as secondary peaks, and really making sure that we can maximize the benefits and minimize the costs to the system. And finally, DERs can contribute to multiple use cases, whether that's feeder versus bulk system peak, or capacity versus ancillary services. There's a lot of interaction between the different options that they can provide, which all needs to be taken into account. Finally, potential depends both on uptake as well as participation, particularly when we're looking at behind the meter resources, which may be driven by customer decision making. And there's a key distinction to make here between simple uptake of a technology, so the customer's decision to invest in and adopt something, versus participation, so actually deciding to participate in markets or programs, enroll in a DR program, and participate in an event, for example. So our modeling needs to account for these various drivers of customer decision making in order to capture the achievable potential on the system. Another important aspect of planning is not only understanding when, where, and how many DERs could show up, but really having a view of what the benefits and costs could be to the system. And so this requires evaluation frameworks that appropriately capture the benefits and costs of DERs. And we see three kind of critical steps to an approach that properly captures DER value. The first is to start from unmitigated load forecasts. So if we have load forecasts which already integrate an assumed load management, it's already getting difficult to capture the value that DERs can bring. The second is a need to move away from a siloed approach to a more holistic framework that can account for all of the different values that DERs can bring across various system levels. And the last one is to reflect the fact that the potential, but also value, is both location and time sensitive. So we need to have an appropriate temporal and spatial granularity in our assessments. So considering kind of the full value stack that DERs can provide, in more traditional energy efficiency assessments, we were maybe capturing only a portion of this, looking mainly at energy and maybe a part of capacity. There's definitely growing recognition for all of the other services that DERs can provide, ancillary services, services across different grid levels, customer applications, as well as some societal and non-energy benefits. But there are still challenges to actually fully integrating all of these value streams, and sometimes a more siloed approach is taken where, for example, we're maybe only capturing their impact on bulk system needs and missing out on some of the distribution level impacts. So we really need to take a holistic approach in order to capture this full value stack. And doing this can significantly improve the business case for DERs. But this isn't without its challenges, because some of these are difficult to quantify, for example, non-energy benefits. And we still need to take into account the kind of competing interaction between different system levels, as well as the location and time dependency of these resources. So diving a little bit more into the time dependency piece, it's important to recognize that system needs will evolve over time, and to take into account both the gross and net load curves, because it's not only the demand side that's going to change over time, but also the supply side, as we're integrating not only more heat pumps and EVs, but also more variable renewables into the energy mix. And so in the graph you can see here, with more renewables in the energy mix, net peak starts to shift to later in the evening. And this is important to take into account because, for example, now we need to be valuing and deploying DERs that meet an 8 p.m. peak versus a 5 p.m. peak to really extract benefits to the system. So evaluation of DERs for capacity in the case of this graph needs to evolve with time and account for these changing system dynamics. The second piece that I mentioned is location is critical. So the value of DERs, especially if we're thinking about the distribution system, is very location specific. The value of, for example, having thermal storage with your heat pump isn't going to be the same on a feeder that's winter peaking and close to overloading as it is on a feeder that's already summer peaking and has a lot of room. So granular forecasts of both load and DER potential can help us to better capture this value and assess DERs on a more equal basis to potentially other solutions like infrastructure deployment. And it can also help on the planning side for utilities to kind of place and prioritize DERs where they will actually provide the most value to the system, and on the other hand, minimize costs. So overall, I think we've seen across the whole panel that DRs can provide an interesting solution to emerging needs and a unique value proposition, but there are still barriers. What I'm hoping to leave you with is the idea that effective planning can help to reduce these barriers and support in unlocking the potential of DERs. But to do this, we need a more nuanced approach to potential assessment that takes into account the location and time-sensitive impacts, diverse load shapes and interactions between different technologies and multiple, sometimes competing use cases, as well as a more holistic evaluation frameworks that consider and allow us to capture the full value stack that DRs have to offer. And of course, much more, but that's all I have time for today.
Hey, thank you, Amara. So we will now shift into the question discussion part of the event. And I believe there are mics, so if people want to ask questions in person, please do. But I have a number of questions already, so let me dive into them. The first and currently most popular question is about distribution grid capacity maps, kind of where are they? And I'm going to start with an Ontario answer, and then I'm going to throw to the group. So in Ontario, the Ontario Energy Board recently directed all local utilities to produce capacity maps, and they have to be up mid next year. My colleague, Onisfi, who's in the group somewhere, is working diligently on this project. And I see that Alex Prior is also in the audience from CanMet, and he has also been working on different ways of making these capacity maps more effective and true. So Demi was the person who asked the question. Go talk to Alex after the session. But I wonder if Michael, you want to comment if you've worked in this area on any of the challenges in producing these maps. And Jeremy, I don't know if you've worked on capacity maps, but Michael, over to you.
So at Hydro Ottawa, we are following that OEB mandate for the capacity maps by March 5th of next year. There are definitely some challenges with producing those. It's a very dynamic system. As we move to decarbonization and the significant increase in load through electrification, capacity on the system is going to quickly be taken up. And so capacity maps, though they are very useful for proponents and let's say for installing EV chargers or siting DER projects, the fact that from the utility side, we aren't able to have necessarily a real-time feedback loop, then even some of the utilities in the United States that have kind of really pushed the boundaries on maps that are available to customers, there's still some limitations to them, and there's still that dialogue required with the utility. So though Hydro Ottawa is working on the capacity maps as per the OEB mandate, we do feel that it's that dialogue with developers, with EV owners and DR proponents, that dialogue with the utility and seeing where there's synergies possible. And if, let's say, there's a system upgrade required, ensuring that we're doing a cost-effective approach that encompasses any future developments in the area. So the maps is one of the tools, but I think having that dialogue with customers is critical.
Sure. I think what I'll say is hosted capacity maps are, I think, really pushing the data capabilities of a lot of utilities, kind of forcing them to kind of at a foundational level create power flow models at a fidelity and level of quality that hasn't really existed, still doesn't exist, but it's pushing us in that direction. So with that in mind, I think just maybe this audience, one thing to kind of keep in your mind as you're looking at these hosting capacity maps is they can mean very different things because they come from very different levels of quality of a model. Some may have a full 8760 power flow model that's underneath it with a great data pipeline that's updating them on a sort of semi-annual basis, and some might simply be based on a substation capacity with kind of a rule of thumb estimate of what a hosting capacity is for that area.
Excellent, thank you. Okay, now a question for Brian. In the work that you've been doing comparing the subdivisions, have you been looking at bringing in demand response, particularly around EVs, into your math? And I'm going to actually add to the question and ask, have you also been looking at the potential of level 1 charging as opposed to level 2 for some or all of the houses? So impact of DR and level 1 charging.
Uh, The, the example I presented was meant to be a sort of a thought exercise. So that's what's in the existing standards. So how you choose to draw out from that existing standard depends on the scenario you come up with. So I chose to go with the level 2 chargers. Level 1 are in the standard. You could have chosen those and looked at what the impact would have been. So the answer is you could, what scenario is the most reasonable that you believe will be in that subdivision in the future that you need to plan and build for? And that's the real fundamental question. And the real issue there is, when are these loads going to show up and where are they going to show up? Because that's the huge impact on a distribution utility. What do I have to build and where do I have to build it? When do I have to? And those are the questions that we cannot answer now. So if you take a traditional viewpoint, which I'm old, so I take a traditional viewpoint, you build worst case. What's the worst thing that could happen? I'm going to build. And that's what you do. So that's what I presented. But speaking of DERs, I guess the thing that pops to my mind when I think about DERs is the technology is there. We can do it technologically. The question is, will the customers come? Will they participate? And to what level will they participate and at what cost? Because at the end of the day, you all out there and me, we make those decisions. Right now, we decide what we turn on, when we turn it on, when we turn it off in our home, what we're going to run, what we're not going to run, what we're going to plug in, what we're not going to plug in. But what we're asking through load control is basically saying, I want to take that control away from you. I want to put it in the hands of the utility so that they can move that load around and maintain control of their system. How many of us are willing to do that, and to what degree? I would say it's to the degree that it impacts your convenience. My experience with customers, electrical customers, is they want convenience. They want to be able to do what they want to do when they want to do it. So if you want to charge your car from 5 o'clock to 8 o'clock so that you can go curling at 10 o'clock at night, that's your choice. And if I'm going to put a load control on that, are you really going to participate? I don't know. And I think that's the big question mark, is unless it's in a utility-owned resource who can absolutely control it, there are only two ways to get the customers to participate. You regulate them or you incent them. I don't know which way is going to work.
Excellent. Thanks, Brian. I'm going to do a bit of a mashup of questions. We've got a few around using price as a tool and around the use of demand charges, particularly for residential customers where we don't typically have them. Should we be using those as a way to discipline customers? And I'm going to kind of, Jotham, throw this at you, because I know my compatriot from the utility sector, we don't set rates, it's the OEB. So I'm going to go to you modelers. So Jotham, are you at all thinking about demand charges in your modeling as a way to manage?
Yeah, so one thing I'd say is I wouldn't call it disciplining our customers. I'd call it incentivizing customers. And I think that the main thing that our model has shown is that there's a lot of value in enabling utilities to be able to move load around. So you can see a substantive reduction in peak load that leads to a reduction in electricity system costs, which then can get distributed in some way. We haven't at this point looked at the extent to which utilities could potentially reduce electricity rates for people that are willing to participate in that program, but it's significant.
The current trending most question, I'm going to go. Oh.
Yeah, I can jump in on that as well. I mean, I think we have done some work looking at potential impacts of demand charges for residential customers, and it could be one effective tool, but I think it's kind of challenging to apply that rate type to that customer class who isn't used to it. And so there's a lot of kind of implementation challenges with that side. There's, of course, a lot of other rate-based tools that we've also looked into around time of use rates, around, how specifically on the solar side, the value of solar and kind of shifting away from net metering to more value of solar tariffs. So I think, yeah, there is definitely a lot of interesting things that we can do with rate design. It maybe needs to still come along with utility-controlled device programs, though, because if you think about a time of use rate, There's nothing really, if the price drops after 8 p.m., there's nothing stopping all of the customers from coming and plugging in their vehicle right at 8 p.m. and then leading to, again, kind of a secondary peak formation. So kind of the interplay between, I would say, rate mechanisms as well as utility controlled programs is important to consider.
Excellent, thank you. And I now barely see that there are people. So over on this mic.
I'll let Greg go second. Thanks. Great presentation. Much appreciated, Philip Doust. You talked a lot about some of the things that keep us utility planners and people in operations up at night in terms of the changes to our grid. Question I have comes back to modeling, specifically about DLMP, dynamic locational marginal pricing. To link that together for those is like, we talked a little bit about net zero being a big target. That will mean a lot of system costs to get there. Part of those system costs is trying to manage that peak load that we have. Getting to that peak load managed means putting in a distribution, a DERMS management system. And again, back to what we were just saying about the pricing aspect and incentives, that's where taking into account the location and amount of energy that's out there, using a dynamic locational marginal pricing system to help incentivize customers. Do you folks see that that is something in the modeling world that needs more work and something that we can really leverage as a tool to help us solve this big question?
Jeremy, do you want to lead off on that one? No, the answer is no.
I think the modeling is much further along here than the policy. I think there are major regulatory hurdles to being able to put forth a system where you have distribution LMPs, right? You have to kind of go back to the bone bright principles of what makes a good tariff, and equity is kind of right at the top of the list. And I have concerns about like equity, right? And having different customers getting different compensation for where they are on the system, and the fairness of all of that. So I think it's less of a modeling issue and more of like, is this something that regulators would actually implement?
Something else I'd like to put into the mix on that is that I think somewhat intrinsic in that assumption is that the locational marginal pricing for a specific location won't change specifically over time due to the physics of the system. But the distribution system is completely different than the transmission system. The distribution system changes its physical open points daily. And that is a huge problem when you're trying to come up with pricing for customers, because I may have to switch out a location tonight. If I lose an underground cable out of a station tonight, I'm now going to feed all those customers from a completely different station, which may have a completely different locational marginal pricing underlying model, and surprise those customers with new costs that they hadn't really anticipated. It's really complicated in that.
Brian, thank you for bringing that practical complexity. I think that's why we need to focus on the distribution system. There is a question over here.
Thanks, everybody. Greg Robart, Smart Grid Innovation Network. So along the theme of customers pricing and all that, and Brian, you just mentioned a neat stream of another complexity, that the distribution system is not stable. But neither are most consumers, and I don't mean that in an irrational way. But how do you build into your models in a distributed energy resource heavy environment where the assets are owned by the consumers in a lot of cases? We can model an electrical system fairly easily. We know how to do that. We've known how to do that for a long time. But how do you model an operating system where human behavior is a really significant piece of how the system actually functions? And it's a question to anybody on the panel.
Amara, do you want to start that one off?
Sure. I would love for some other people to chime in, because to be honest, we're not kind of going all the way down to the day-to-day operational aspect. So maybe some of the distribution system engineers want to chime in on that. But it also relates to what I touched on from a potential perspective. Yeah, exactly that. I mean, customer behavior does play a huge role in terms of understanding how much potential you actually have out there from day to day, and then how much you're actually going to get on a given, DR event or, at an operational basis. So this is a really important aspect to layer in, all the way from the potential assessment down to the operational level. And I think it's also something that kind of needs further work and understanding to really know how customers will behave and be able to integrate that into our models and systems even better.
Michael or Brian, do you want to add on?
I mean, Amara, you kind of covered it all from our perspective, behavior-wise. There's only so much modeling we can do before we have to make assumptions on what can we actually dispatch, what can we count on if it's needed as a resource out on the system. And to Brian's point, in terms of how dynamic the system is, even from something as simple as connecting a DER, we'll have a contract in place for a specific feeder that customer is connected to. But if now we're shifting the system and they're expected to be connected to a different feeder that may have a constraint, it's not as simple as just transferring them over onto that feeder. So there's a behavior component and expectations from the customer about what the utility can provide. But from the utility's perspective, we have to ensure the reliable and safe operation of the grid, and that is paramount.
If I could just add one thing to that as well. I mean, I think it's a great question, and we're certainly struggling with this. I know that the approach that we've taken to characterize how willing people will be to participate in a program is that we've participated in one study in which we surveyed people. I was indirectly connected with the study, but we've participated in one study in which we surveyed people on how likely they would be to participate in a utility-controlled charging program, subject to different, changes in rate structure. And I think what's really lacking from this is that we don't have a lot of real life data to be able to go see whether or not those assumptions that we're currently using are correct. So I think that we're doing our best to try and represent that within our models, but I think there's a lot of uncertainty. I think as data becomes more available, hopefully we can better parameterize how households and firms will or whether or not they'll be willing to participate in these programs.
Yep. I think one of the things the modeling community could help with here is a risk assessment model. I mean, that's really what it boils down to, is how probable is it that when I need that resource will be available. If I build big enough wires and put in enough transformers, I can guarantee you they'll be there when I need them. But can I guarantee that the resource that you're describing, the NWA, will be available when I need it for what I need it for? And somehow we need to have better risk assessment tools, because I'll tell you, as a distribution engineer, we're risk averse to the nth degree. Build it so that the lights can't go out. Customers want two things: keep the rates low and keep the lights on. And I do not get phone calls at home telling me, thanks for leaving the lights on and keeping my rates low. But I get phone calls at home saying, the lights are off. What the heck are you doing?
Jeremy.
Yeah, so you beat me to the punch a little bit in mentioning the word risk, right? I think this is something that is very poorly defined on distribution networks and distribution planning, but it's not poorly defined at the transmission level. We have resource adequacy metrics defined there, and I think we ought to be borrowing those concepts and pushing our distribution planners to go beyond saying I won't accept any risk at all to like yeah, I'll accept 1 hour every couple of years kind of risk levels, and then we can start. I think once you introduce risk to the equation, you can start to model DER and compare it to traditional investments in a way that you couldn't before, because they all have risks, just in different times and places, and you need to be able to show that very clearly before you accept new technologies.
Great. Thanks, everybody. And thanks for that question. We have Mark up at the mic.
That might work better. Just a comment I would emphasize, I'm afraid invisibility to the customer is probably absolutely crucial in terms of customer acceptance around load management. But my real question was around, in the electrification scenarios for Spacey in Ontario, for example, as opposed to BC, that load is going to be extremely variable. Like you're talking about a lot of variable load, certainly seasonally, if not more than that. which then begs questions about what would be serving that load? And then how does that affect the rationale for building energy efficiency and DER development?
Jonathan, do you want to start with that? And then maybe it's Amara.
Yeah, sure. You know, I think one thing that's really important to highlight is that achieving net zero really requires a huge transformation of our energy system. And so I haven't presented on what is meeting that load, but I strongly suspect that it is things like solar and wind. And you know, when solar and wind is introduced in a system like Canada, in which we typically have a winter peak, in Ontario, in response to achieving net zero, we see them actually switch from a summer peak to having a winter peak, presents a challenge. And so this raises the importance of other technologies available to shift electricity consumption. So that, and you can do this either on the supply side, so you can use this, you can use, you know, lithium ion batteries, or we see an increasing role actually for seasonal storage in some of our net zero runs. As well as the role for DER technologies. Now, I know that this sounds very, very foreign to everybody in this room. We don't have any of these technologies really being deployed on this scale currently, and everybody's really concerned about what the role for solar will be in provinces in which we have a winter peak. But I do think that achieving net zero is going to require a massive transformation of the electricity system, as well as massive investments. And this is part of it. And I think as we become more familiar with these technologies and as their costs come down, they don't need to be quite as scary as they are today.
I actually don't think I quite caught the end of your question. If you can just repeat so I make sure I touch on it properly.
My question is, what would be serving the load? And in effect, what then is building energy efficiency and DERs potentially displacing? And then how does that affect the use case and the economics?
Okay. Yeah, for sure. Well, I guess this kind of touches on a few of my points. I mean, first of all, yeah, kind of the economics are very time and location dependent. And as we are shifting towards winter peaking, this is going to kind of completely change the value proposition for a lot of DERs and other potential resources on the system. So if we're looking at a winter peaking scenario, it's true that maybe solar isn't providing capacity needs anymore, but it might also be meeting some of the other, I guess, values in that stack. So it can still be providing, energy, environmental, non-energy benefits. So this is kind of the first piece that I would mention that's important to consider. And then, of course, Julia was kind of mentioning before the beginning of the session that it's a pet peeve of hers that she hates when people just refer to DERs, and not kind of driving down further into what does that actually mean. So it could be generation technologies, solar, et cetera, but it can also be storage, it can also be demand response, it can also be energy efficiency. So, some of these can be more well placed to step in and meet some of those winter peaking needs as we're shifting to that scenario.
All right, thanks, Amara. And thanks for flagging my pet peeve. The three-letter acronyms, not so helpful in our space. I do want to, we've got 6 minutes left. Our trending question is for Jotham. Are data centers significant future load in your modeling? How are you thinking about data centers?
As a side note, we work with the government of Ontario, and every year we're required to calibrate our model to the latest IESO forecast. And this last year was actually a bit of an issue for us because they see such a large increase in load coming from data centers. That is actually not included in this analysis here, but when we do our provincial modeling, we do our best to include it. Now that said, I'm maybe not totally familiar with all the nuances of large data centers, but I do think that they tend to be a little bit more base load, which means that they are unlikely to have quite as significant of an impact on peak.
Hello, Serge Bédard, Natural Resources Canada. You spoke today quite a bit about demand response, mostly from a customer perspective or from a residential perspective, I feel. how do you see the potential in industry? When we talk about distribution system, mostly medium-sized company, small, medium-sized company, but is it something you have accounted for or model in your analysis, or you mostly consider industry as a base load, which is not really always the case? Thank you.
I wonder if that's Jeremy and Jotham again.
It is, I haven't done a lot of modeling in this space, so I might turn it over to Jotham, but I think industry demand response is generally a little bit easier to predict. And that's why we've been focusing more on the residential side, because it's kind of a harder thing to model. There's more unknown. So I do think this is something that, because they get incentivized in ways to sort of to be there, or penalized if they're not providing demand response when required. That's a little bit easier to work into a model. I don't know if you have anything to add.
Yeah, I mean, for transparency, the vast majority of industrial load in our model is just considered to be base load and doesn't change a huge amount or is not responsive to policy signal or price signals. We do have a couple of sectors in which we're simulating interruptible industrial loads, but to be honest, they're hard for us to model because we need to understand exactly how those systems work. And so there's a few sectors where we think they're ideal. That's really, I mean, hydrogen production is actually one of the key ones where we can simulate industrial or interruptible industrial loads, but we haven't gone as far as I'd like.
I would also add to that, we do definitely also consider industrial load when we're looking at DR potential assessments, and there is a lot of potential in that sector. Agreed that I guess maybe it's a little bit more certain and there's more well-established methods for how to capture that. So maybe it was a little bit less of the focus today, but definitely should not be downplayed. And yeah, there's a lot to consider in terms of kind of developing, I would say, sort of customized solutions or measures in the modeling that take into account the uniqueness of industrial facilities and the industrial landscape of different jurisdictions that we look into.
All right. I've got now a question for Michael, a quite specific one, and that is, in the modeling work you guys have been doing, have you taken into consideration the degradation in EV battery performance during cold weather?
We didn't specifically look at the degradation. It was more so the range impact. I'm not sure if they're talking about the life of the battery.
That's what I mean.
Oh, okay,
Like
for
that
range.
you're going to be charging for.
Yes, so we worked with a third-party consultant who had some proprietary information on charging profiles. And so they provided that as a feed into the model in terms of what we could potentially see in increase or shift in the EV charging peak and profile itself with respect to a significant decrease in range for both light-duty, medium, and heavy-duty vehicles. We also worked with the city of Ottawa, who has a EV bus fleet that they're rolling out in terms of some of their pilot information that they received for charging profiles in the winter.
Okay, I think we have time for one more. I would note there are a lot of really excellent questions here, so folks go in after or come and find our panelists. Oh, there's Mike. Fantastic.
Thank you very much. Leonard Oline from the University of Calgary. In Alberta, we have interesting changes going on where we are expecting to allow a lot more congestion on the transmission system while getting rid of the credit for distributed generation. And I'm wondering to what extent the modeling that you're doing or the analysis you're doing is able to help identify the value of both generation at the distribution level, but all the other changes you're making at the distribution level to help manage load and bring value to the system. And how close are we able to bring good information to regulators and politicians about the value that the distribution system brings?
Amara, did you want to start with that one?
Yeah, I think that's a super interesting question, and I guess exactly what some of the modeling that we're doing is trying to get at, where we're really kind of driving down to maybe the substation or feeder level of the distribution system, taking into account the unique load curves and shapes and different technologies that might be present on each of these, in order to build like a unique value stack, I guess, at each location in the distribution grid. And this can, I guess, could be leveraged, I would say, to assess what the value could be of distributed generation or, all of the other solutions that I mentioned. In terms of the second part of your question around how ready we are to kind of bring this to policymakers and regulatory teams, I think, a lot of the frameworks that we're leveraging are robust. For example, it's similar to some work that I mentioned that's being done on the value of solar and establishing value of solar tariffs, which has been presented in front of regulators and has sometimes considered a specific locational value behind that. So I think we're definitely moving in that direction, but it still needs to be kind of expanded, applied to other types of DERs, and yeah.
Excellent. Thanks, Samara. We're now into the 23 seconds of shame. So I want to thank Brian, Michael, Jeremy, Jotham, Amara, and all of you for a really engaging conversation. We hope it was so engaging that Edward will bring us back in some configuration next year. So thank you very much.